Okay, so today we're going to talk about projections, which are super cool. And when I was a kid, all I wanted to do was make a 3D video game. Like when I was 7, I was obsessed with graphics, and I would spend all day taking pieces of paper and drawing lines and trying to bang my head against all this math I didn't know yet of how do you take a 3D point and turn it into a 2D point on a screen. And it's too bad I didn't have anyone to ask because it's actually not that hard to do. And projections are, you know, really how we take 3D and turn it into 2D so that we can see it on a screen. Or, in fact, it's how we take 3D and turn it into 2D so we can create, say, a shadow map or even a video game that's only in 2D. In fact, it generalizes to all dimensions. And in fact, later in this course, we'll be talking about the separation axis theorem, which is a projection of an object down into one plane, into one dimension, which is a way for us to then determine whether or not it's it's colliding with another object. So let's kind of get into it and talk a little bit about what is a projection. Like, what are we really talking about, right? So, oops. Take this image, for example. What is it? Obviously, we look at it and we see what looks like a cube. That's what our brain tells us. But if you kind of mess with your mind, you can look at it and you can say, oh, is it a cube that is, where the front face is on the left or the front face is on the right, right? Based on what we can kind of almost shift it in your mind. If you take a look at one face and you look at the other face, you can kind of almost force your mind to see one face in front of the other. So what you're seeing isn't a cube. You're seeing a 2D projection of a cube. But in reality, it could be just a variety of shapes. A bunch of different shapes that are lined up. And if you've ever played with those little kind of toys where you can kind of take them and make different shapes, you can make things that look like cubes, but in reality, they're just flat. They're flat objects. So let's take another example. This looks like a hexagon, and however, if we change the shading of each of the sides, now this looks a lot more like a cube, which is interesting. A projection is just a way for us to take information and represent it in a way that lines up with lesser dimensional information. The first experience many of us have with this is with our own shadows. We look down and it's like a 2D version of us. Right? Our shadow can be bigger than us, it can be smaller, it can do funny things, and you can even make it do shadow puppets and do some really fun things with it. So the projection that you have of a particular thing is going to be dependent on your perspective. That's, I think, a very, very important thing. For example, in the context of this shadow, I'm looking at this shadow, but the person who is looking at this shadow is going to see a different thing. For example, the idea here is depending on your perspective, depending on where you're looking from, the projection can make you see different things, like this optical illusion. Another example of this is this optical illusion where when you move the camera, you would kind of see it looks like the dinosaur is moving their head, but if we take a look at what's actually going on, right, all of a sudden you'll see that actually we've all been tricked. It's not moving at all. Here's another example of the same idea. It kind of looks like a square, like a floating cube, but really it's just a piece of paper that's concave. A really good example of this, what's called forced perspective, is in the movie Lord of the Rings, where they had these small little, hobbits, which were mini people, but not small people. They were just smaller people, and they used forced perspective to create that illusion. But something that's really hard with forced perspective, as you saw in these previous examples, if you move, things kind of look a little bit funny, right? Things start to kind of not make sense at a certain point. And with forced perspective, you have that problem. So let's take a quick look at it. It's kind of a fun thing.
What we've done with some of our forced perspective shots is be able to move the camera for the first time. That they were always techniques that required the camera to be locked off, because once you started to move the camera, it would give away the illusion of one person being further away when you're really wanting them to look like they're side by side.
In order to get the camera alive, we started thinking about ways of using motion control in order to doing what we call moving forced perspective shots using slave motion control bases.
You do a motion control move where you have the one actor on a moving platform. So when the camera moves, you're doing your moves all relative. So you're literally sliding the guy along on the floor as your motion control motion control camera is moving along.
You have the camera on a motion control dolly, making it move in and out or side to side. But you have another smaller dolly that's electronically hooked to it and does the exact same motion, but sort of in a counter movement. But every time you move one way on one dolly, the other one immediately responds.
When you're actually viewing it, you're basically doing a split. And if you're doing a move around, when you do this split, it looks like they're moving in sync with each other. And it's because you're moving the two guys around relative to this moving camera.
In the shot where Frodo is pouring tea for Gandalf at a table, and the camera kind of crabs past from one side of the table to the other side. And in that instance, Ian McKellen was actually sitting on a dolly that was actually moving him slightly on a small scale table with small scale props. And it was not too far from a full-size table, a Frodo-sized table with larger Frodo-sized props.
I've got a look there.
For when he's standing?
Yeah, but I don't, and I got looks there for when Elijah's sitting. What I don't have is a look when he's crouching, which is the beginning of the shot.
Okay, we can give you that. We can go back to number ones and make sure that you've got that.
Through camera, at one end of the move, everything lines up. When you move to the other end of the track, everything still lines up because that smaller table and Ian McKellen on that other dolly has moved slightly.
It's kind of fun to actually build these things and see them in camera. It's wonderful. It's fun to actually just get dailies back and the shots done.
It worked pretty seamlessly, and everyone was really amazed with the result.
The fires of Mount Doom, taken by Isildur from the hand of...
So you can kind of see how amazing that movie is in that context. The amount of work, every single shot where you have two people, that one's a full-size person, one's not a full-size person, was actually a complete motion control system. But it kind of shows the power of these solutions where you can do pretty amazing effects without any computer-controlled dollies, I suppose, but no actual CG in that sense. It was a real thing. Whatever, cool stuff. Moving on. So this kind of demonstrates this effect. It's been used into some pretty great effect by some fun video games like Monument Valley, for example, where you can use these effects to really grate the light factor in video games. Originally projection came from artists' determination to represent the real world in the way that it is. And if you look at early art, like I think in the pre-Renaissance art has not much of a sense of perspective and not to the sense of projection, and that art is more representative of the feeling, of the emotion. I'm not an art person, I don't really know, but generally speaking, you see this behavior, you see this sort of thing emerging out of the kind of Renaissance, and Leonardo da Vinci is credited for a lot of work with projection and so on. So yeah, these are some great videos in talking about fourth dimensions and projections of the fourth dimension to the third dimension. Suggest you guys check it out if you'd like. This is a really great example, for example, of imagine if toys were in 4D, right? These are like cubes that are
4D toys is a toy.
Whoops. That are projected into the fourth. This is a 3D projection of the fourth dimension, almost like a 3D cross section of it. So pretty fun. And this is a really fun game that's currently in development still, I believe. This video is from 2014, but demonstrates some really interesting examples of imagine a game that you play in 3D, but you can also go into the fourth dimension to sort of, let's say you want to go through this wall, you were able to do so by effectively walking into the fourth dimension. Then that way you can sort of navigate dimensions to kind of get across different things. So recommend checking out that video in the slides if you're interested in it. So we're going to talk about a couple of different projections. There are different forms of projection. The first one we're going to talk about is the orthographic projection. And the orthographic projection is really simple in that you're taking the 3D information and you're eliminating one of the dimensions. So first you take your data and imagine you're already in your view position. So you're from the perspective of the camera, you're looking straight out into Z, and all you're doing is everything that you see from that perspective loses its Z value. And so an object that is 2x, 2y, and 2x is now at 2, and so on. And maybe you're scaling it down to the clipping plane, which is what OpenGL uses, which is that 1 to -1 that we've talked about. And so the orthographic projection is almost like taking a cube and applying it to your to the place in front of you, and then that's what you're looking at. So you're clipping at those things. And if you think about just an example, a calculation like your respective y that you see on your near plane or on your projection plane, which is represented by n in this line here, all that is equal to is just that y. So the y value becomes the y value, and you eliminate the z. So when you look at the orthographic projection, often it looks a lot more like an identity matrix without the z component, but with a scaling down. So you're taking that and turning it into a -1, 1, -1, 1, and so on. Now, that's pretty cool. We have our view volume. Say we wanted to create more of a, like a view, like a perspective. So if you think about what a perspective is if I were looking from a particular point in space out, the line isn't straight like this. Like an orthographic projection is representative of things that are so far away that the direction of them no longer really matter. Like for example, if you look out at the stars of the sky, your position, your movement in your position is not going to affect their position very much. And so you can almost think of your view into space, your view at the sun, as a orthographic projection. So say tomorrow the moon had a big dot on it, you would see it almost with an orthographic projection just because those lines, by the time that they get to you, are so straight, they might as well be straight. And if you think about directional lighting, like for example, lighting of the sun, when you look at a shadow, it doesn't look like it kind of flares out. It's just sort of a set thing. But with the perspective, when I look at something that's far away, it's smaller than something that's close up if it's the same size. As we saw with force projection, you can use this effect to great effect for creative things. But what that means is that as I go farther out, I can see more, and that's what kind of creates that view, what's called a frustum. A frustum that is effectively like a trapezoidal volume, or like a triangle with its top chopped off. And to talk about a little bit about the syntax of this, the plane close to us on the view frustum is the near plane. The far plane is what's called the far plane. And then you've got the top, the bottom, the left, and the right. And oftentimes you don't really deal with top, bottom, left, and right. You just deal with width and height. And often you've heard about what's called the field of view. And the field of view is really just, if you think about that point and the distance between the point and that near plane and the width of that near plane, that angle that's produced is the field of view. As you can imagine, transforming or changing that view, if you wanted to have a very high zoom, you would make it smaller so you'd see more of what's farther away. If you want to have a near view, a wide angle being a high field of view, meaning a very close near plane, right? So this is a kind of a good thing to kind of get a feel for, where you're taking this information and you're converting it from what is a just three-dimensional space, and then transforming that into it. And you keep on hearing me say transforming. That's because that's exactly what a projection is. A projection is a transformation, no different than the translation or the rotation transformations that we've been talking about. And so you'll often see in a shader what's called the MVP, the model, view, and projection matrix. And it's just one matrix, and it's the combination of the model times the view times the projection matrix. Well, usually projection, view, model, because the data is on the right side. Depends on your convention. But either way, you can kind of see. So the perspective, as we were talking about, you've got the front plane, which also is the clipping plane, and that's true for both orthographic and perspective. Anything outside of your view frustum is effectively clipped, so you're not going to render anything outside of that. And that's why you apply this transformation at the vertex stage, because you want to apply this transformation before you get to the pixel shader, because you don't want the pixel shader operating on fragments that are outside of your projection volume. Right? It's just a waste of time. If you have a triangle that's to the right of the screen, you don't want to waste that. Like, see where my hand is. Right? I'm rendering my hand, but as soon as I go out of the projection volume, I don't need to render my pinky. That'd be just a waste of time to do. So let's save that computation for more important things. So you can kind of see here the way that this would look is you have like a volume that's applied to your thing, and the math is actually quite simple. Obviously, applied to a linear algebra matrix and creating that transformation gets a little bit more sophisticated than what I'm representing here. However, this is actually pretty much the math, where you draw a line and you have these two triangles. The zero, the origin to y, is that's one triangle, that one right angle represented by 0 to y, y to z. Then you have another right triangle, like right angle triangle, which is 0 to y prime down to the near field. And so to get to y prime, you just have similar triangles in that equation, and then y prime is equal to the near field times the y divided by the depth of that point. And where do you get the depth? Well, again, remember that you are sitting at 0 looking down the z-axis by virtue of the view transformation that you've already applied to all of your stuff. So everything's in front of you, and so every vertex, every point is just going to have a depth value already. So that's why you are utilizing the z of the point to get its respective projection. And this makes a lot of sense, because the farther away something is, the smaller it should be. And that's represented in this equation, where if something's farther away, you divide it by a bigger number. And that's math, simple math, actually. So let's kind of talk a little bit about the ordering of these matrices. I already mentioned the MVP matrix and that transformation that represents what an ultimate point on the screen looks like. So we start off with model space, right? Model space is you've got a vertex that has a position respective to the origin of the model. At this point, we haven't transformed this or anything, but the model now has a location and orientation. That takes us to world space. So when you take your model and you apply to it a model matrix, which represents its translation and its rotation and scale, now that object is in world space. World space is not necessarily what the camera sees. That's what we see. Like if there's a tree at x5, y5, that's what we're talking about, world space. But if I'm sitting at 0, that's 5, 5. But if I'm at 3, that's 2, 5, right? So world space is not view space, and that's like a big thing that you have to kind of remember. So when you're taking the model to the world, you're applying this model matrix, and it takes you to your world coordinates. Now imagine you have a camera, right? You can see that in this image, the origin, the monkey is like away from the origin, but so is our camera. So what we want to do is we want to hop. We want to do this sort of the same transformation. We want to apply the inverse transformation of our camera to the model, such that it's almost like we're taking our camera, which is at a position x3, right? And we want to apply to it -3 to put it at 0. So we're inversing its transformation. And what that will do is it will then put our monkey not just 2 away from the matrix, but actually 5 away from the origin, because our camera is moving there and the monkey has to kind of move with it. So that's what's called the view matrix, and the view matrix tends to be the inverse of the camera's location and rotation and all of that stuff. Now finally, now we have the camera looking down the z-axis, seeing everything in front of it. We are now in what's called the view coordinate system. And now we want to take that and turn it into the projection view, right? So if you imagine we're doing orthographic, we would just remove the z. It's almost like taking the image and like basically pasting it onto a window in front of us, like by drawing straight lines. But with a projection, you can see this sort of frustum that then kind of things that are farther away get smaller, and that projection will then get applied to this thing. So you apply that projection matrix, and then you get what you would see on the near plane. Again, so that is, you know, some would call it homogeneous coordinates. You can call it the screen coordinates as well. It's also used. There's a lot of ways to kind of describe this. But you can see this model view projection in that order, or MVP. That's the way we go from a vertex in a model all the way to the point on the screen that vertex represents. Yeah, so projection, actually, math gets a bit complex, but not that bad, and really allows us to create 3D projections of things, and is at the core of everything that we do. And there's a lot of different parameters here. Like if you're doing something for VR, you may have projection matrices that don't have a 0, right? It's not the width, and the left and the right are not equivalent, so you're not doing width and height. It's slightly different because one eye is looking this way. You have this sort of thing. So the math, if you're ever kind of concerned or worried about if you're doing it correctly, just look it up. There's a lot of information about this out there. But ultimately, at the core of it, it's just about creating those similar triangles and just applying these transformations that we're already relatively familiar with to get to where we want to be and get a point in a model to the point on the screen.